Hey, good morning, sir. Good day. So today I'm going to present my five articles that I have selected. It actually talks about the scaling of predictive analytics in high dimensional big data. So it's all about navigating the shift from traditional regression to scalable deep learning. So it's all about optimizing for accuracy, scalability, and interpretability across finance, cardiology, and clinical anesthesia. So the breaking point of traditional data processing. So we have here the high dimensional reality. The explosion of volume, velocity, and variety fundamentally alters predictive modeling. So the baseline here is all about traditional machine learning excels at structured, linear datasets but plateaus as dimensionality scales. So the catalyst is distributed computational frameworks such as Apache Spark, TensorFlow, PyTorch now allow us to ingest unstructured text, images, and high frequency time series. So the dilemma, however, is that training deep architectures on petabyte scale datasets requires massive computational overhead, risking gradient explosion and convergence instability. Yeah. So next we have here the iron triangle of predictive analytics. So algorithm selection in big data is a continuous navigation of three competing forces. So we have here interpretability, scalability, and predictive power. So every model sacrifices one dimension to optimize the others. And so when you talk about interpretability, so the transparency required to trace exactly how a model reached its decision, or what we call as critical for compliance and clinical trust. For scalability, however, is the ability to train efficiently on 1 million plus samples without hitting exponential computational bottlenecks. And for predictive power, it is the capacity to capture highly complex, nonlinear dependencies in unstructured data. Okay. So mapping algorithm against dimensional constraints. So we have here the algorithm showdown matrix that shows the handling nonlinearity, feature extraction, scalability ceiling, and interpretability. So when you talk about linear or logistic regression, it's weak when it comes to handling nonlinearity, and its feature extraction is manual, scalability ceiling is medium, and interpretability is high. For random forest or SVM, it's moderate when it comes to handling nonlinearity. Feature extraction is manual also. And when you talk about scalability ceiling, it's 1 million samples. It causes bottleneck, and for interpretability, it's moderate. For DNN or deep neural networks or CNN also, it's high when it comes to handling nonlinearity. Its feature extraction is automatic, and scalability ceiling is high with GPUs. And when it comes to interpretability, it's low, or what we call as black box. And lastly, for hybrid CNN or LSTM, it's exceptional in handling nonlinearity, and feature extraction is auto-temporal or spatial. And when it comes to scalability ceiling, it's unlimited. Its interpretability is very low. Okay. So for the exponential slowdown of traditional machine learning that talks about scalability ceiling, as datasets expand, three baselines and SVMs encounter a hard computational limit due to memory overhead and iterative complexity. So we can see here that the deep architecture's parallelization over GPU clusters limits time increases, highlighting the necessity of deep learning for massive data sets. And so we have here the SBM training time that has the higher minutes, and next one is RF training time, and down to CNN training time that has the lower time of all the training times that we have here. Okay. So the tactical playbook for domain-specific applications. So when decisions require absolute transparency, traditional models remain the weapon of choice. So we have here three domains that reflects the five articles that I have selected. So we have the domain one to be, it's all about SME credit finance. And for the domain two, we have cardiology or CVD risk. And for the domain three, we have clinical anesthesia. So for the domain one, its algorithm is big data driven logistic regression, and its goal is to have binary default prediction using aggregated financial behavior. For the domain 2, its algorithm it uses lasso regression, and its goal is all about multi-collinear variable selection to isolate distinct dyslipidemia biomarkers. For the domain 3 that talks about clinical anesthesia, its algorithm is multi-level regression. Its goal is all about isolating practice variability across clustered patient provider hospital structures. Okay. The next one, so we have here predicting SME credit default through logistic regression. This talks about the domain one earlier. So in financial risk management, the why is just as important as the what. So logistic regression provides a transparent calculation of compliance probability. So we have here the diagram, yan, and we have here the key predictive ratios. So we have here the input-output cancelled invoices. Yan. So cancelled invoices, net invoice amount, coefficient of variation, capital turnover, and credit history to be lower ratios directly correlate to higher credit worthiness. And for the coefficient of variation of invoice amount, we have here measures revenue deviation, smaller coefficients, indicate stable earnings and lower credit risk. And for the capital turnover rate, higher efficiency translates mathematically to a lower probability of default. Yeah. So next one we have the lasso sieve, filtering multicollinear CBD biomarkers. Yan. So in dyslipidemia and cardiovascular disease or CVD research, biomarkers are highly correlated. So traditional regression overfits. So we have here the lasso filters that is being displayed. So for the L1 penalty or L1 regularization, it imposes a penalty on the absolute values of regression coefficients. So effectively shrinking redundant variables. Like for example, total cholesterol and LDL-C to zero. And while the other one, the Framingham result, the model retains HDL-C and systolic blood pressure as core predictors, discarding variables that offer no additional predictive value. Yeah. So the next one, it's all about selecting the right tool for clinical variable selection. So we have three here. We have lasso regression, random forest, and elastic net. For lasso regression, its model type is linear model. Variable selection is explicit. Handling multicollinearity is limited. We select only one among correlated predictors, and its interpretability is high. Capturing complex relationships is limited. So this also talks about the earlier slide about lasso regression. For random forests, we have the model type to be nonlinear ensemble method, and variable selection is implicit through feature importance. And handling multicollinearity is good, less sensitive to multicollinearity, and interpretability is moderate to low. Capturing complex relationships is strong. For the elastic net, we have here the model type to be linear model. Variable selection is explicit. Handling multicollinearity is strong. Can retain correlated variables and interpretability moderate. Capturing complex relationships moderate also. Okay. For the hidden architecture of clustered clinical data. So standard deviation assumes all data points are independent. In clinical anesthesia, this assumption fails completely. And so we have the label one with regards to the patients, and level two is the hospital level, and level three is the region level, which has the highest level. So the multi-level reality Patient outcomes, example mortality, preeclampsia, are linked to the specific practitioners treating them and the unique systemic practices of the hospitals they occupy. Okay. For the quantifying the invisible forces of practice variability, we have multi-level regression provides the metrics to measure the exact influence of hospitals' specific culture and practices. So we have here low variance and high variance. It talks about intra-class correlation coefficient or ICC and median odds ratio or MOR. Okay. So how about translating variance to risk with the interval odds ratio? So the interval odds ratio or IORAT, once hospital variability is established, we must evaluate the specific cluster level policies, such as the threshold for admitting pregnant women to the ICU. So we have here the lower bound, distribution of odds or odds ratio, and upper bound. So the IORAT provides an interval that covers the middle 80% of the odds ratio distribution between two clusters with different covariate values. If the interval does not include one, the association between the hospital's ICU admission practice and patient mortality is statistically significant isolated from patient level confounding. And so breaking the dimensional ceiling with deep architectures, when data dimensionality explodes, incorporating high frequency IoT sensors, raw text, and massive unstructured logs, traditional regression collapses under feature redundancy and data sparsity. So to capture nonlinear relationships of petabyte scale, we must abandon manual feature extraction and embrace deep neural networks deployed across distributed computing environments. Okay, so the architecture engine. So we have here the hybrid CNN LSTM. So we have three layers, CNN layer, LSTM layer, and the result. Okay, so we have here CNN special structure and LSTM temporal sequencer. Okay. And measuring efficiency by the scalability index or SI. The scalability index or SI quantifies resource efficiency in distributed deep learning systems. So as we can see here, the training and validation loss versus epochs. And the benchmark is we have here hybrid architectures deliver a scalability index four times higher than traditional integration baseline. So by dynamically allocating computational resources across GPU clusters, the CNL-LCM architecture achieves an average performance gain of positive 322% in distributed environments, mitigating gradient explosion and training inefficiencies. So key evaluation metrics for high dimensional environments, we have three: continuous regression, discrete classification, and operational scalability. Yeah. The efficient frontier predictive analytics talks about the historical dilemma. The historical dilemma forces a choice between the transparent accuracy of lasso and the opaque power of deep learning. And the bridges, explainable AI frameworks like SHAP and LIME, reverse engineer the black box by visualizing feature influence within deep architectures. So we can deploy highly scalable neural networks into compliance heavy fields like medicine and finance. And the horizon, distributed intelligence and AutoML. We have here automated machine learning and distributed intelligence. So the imperative energy efficient analytics, as dimensionality expands, the raw computational power required to train deep architecture carries severe environmental and financial costs. So the ultimate measure of a model's elegance is no longer just its predictive accuracy or its scalability, but its efficiency. So the future belongs to resource-conscious hybrid architectures that deliver deep learning performance with a fraction of the GPU hours and carbon footprint. So that wraps off my presentation. So thank you for listening. Okay.